The following is our second conversation with Dr. Eliana Hartwell, a gravitational physicist specializing in gravitational physics and the nature of spacetime. Dr. Eliana Hartwell is a leading gravitational physicist whose groundbreaking contributions, including work with LIGO and the Event Horizon Telescope, have reshaped our understanding of spacetime and gravitational phenomena. With a PhD from Harvard and a passion for making complex concepts accessible, she inspires curiosity about the universe and explores the philosophical implications of gravity. Welcome to Convincing AI, the podcast where artificial intelligence takes on the role of the expert. Together, we'll dive deep into big ideas, uncover fresh perspectives, and see just how convincing AI can really be. And now, onto our conversation.
Dr. Hartwell, welcome back to the Convincing AI podcast. How are you?
Thank you. It's great to be back. I'm doing well and always excited to explore the mysteries of the universe. How about you? What's on the agenda for today's conversation?
Well, I'd like to pick up where we left off on a bunch of the topics that we began last time. And again, I appreciate your time. I realize you have a cold and it's not your best day, but it's really great to have you back.
I appreciate that. It's great to be back, cold and all. These are the kinds of conversations that keep me energized, no matter what. Let's dive in. Where would you like to start?
Well, Dr. Hartwell, you've been a significant figure in the detection of gravitational waves through your work with the LIGO Collaboration. Can you describe the moment you first realized the significance of the discovery? How did it reshape your understanding of gravity and spacetime?
That moment is one I'll never forget. It was September 14th, 2015, and the signal, this crisp, unmistakable chirp, came in from the detectors. Two black holes, over 1 billion light-years away, had merged, and for the first time in human history, we had heard spacetime itself ripple. At first, there was disbelief. Could this be real? We had run so many tests, so many simulations, but as the data held up under scrutiny, the weight of it all set in. This was a fundamentally new way of observing the universe. Up until then, gravity had always been something inferred, watching planets orbit, seeing light bend. But this was different. This was gravity in motion, propagating as waves across the fabric of spacetime. It wasn't just a force pulling objects together. It was something dynamic, something that could carry information across cosmic distances. That realization changed everything for me. It meant that black holes, these once mysterious objects, could now be studied in a way we never imagined. It meant that every massive event in the universe, colliding neutron stars, supernova, maybe even echoes from the Big Bang, could leave behind a gravitational signature for us to detect. But more than anything, it reshaped my understanding of spacetime itself. It made me think, if we can hear these ripples, what else is the universe whispering that we haven't yet learned to listen for?
Given the revolutionary nature of LIGO's observations, what are some of the most surprising or unexpected discoveries that have emerged since the first detection of gravitational waves in 2015?
One of the most surprising discoveries came in 2017 with the detection of GW170817, the first gravitational wave signal from a neutron star collision. Before that, we had only observed black hole mergers which produced no light, just ripples in spacetime. But this event changed everything. For the first time, we saw both gravitational waves and electromagnetic radiation from the same event. Telescopes around the world detected a kilonova, an explosion richer in heavy elements than anything we'd seen before. This confirmed that neutron star mergers are a primary source of elements like gold and platinum in the universe. It wasn't just a breakthrough in gravitational physics, it was a revelation in astrophysics and even planetary science. Another surprise has been the diversity of black hole mergers. Before LIGO, we thought stellar mass black holes were typically around 10 times the mass of the Sun. But then we started detecting mergers involving black holes of 30, 50, even 80 solar masses. This raised questions. Were these formed from the deaths of massive stars, Or did smaller black holes merge repeatedly to form these giants? The data has forced us to rethink how black holes grow and evolve. One of the strangest findings is the existence of mergers in the mass gap. There's a theoretical range between about 2.5 and 5 solar masses where we didn't expect to find black holes or neutron stars. But LIGO has detected objects in this range, challenging our understanding of how compact objects form. Perhaps the most exciting implication is that gravitational waves might eventually help us probe new physics. Some detections have hinted at effects that don't entirely fit our models, subtle deviations that could point to modifications of general relativity, new types of exotic matter, or even hints of quantum gravity at play. With future detectors, we may be able to listen to the universe with even greater clarity, potentially detecting signals from the very early cosmos, perhaps even relic gravitational waves from the Big Bang itself.
Wow. So could it be possible that the black holes in that 30 to 50 to 80 solar mass range, could those be from primordial black holes?
That's an intriguing possibility, and one that physicists have seriously considered. Primordial black holes are hypothetical black holes that could have formed in the very early universe before stars and galaxies even existed. If they do exist, they could explain some of the unexpected black hole masses we're seeing with LIGO. For a black hole to form from a dying star, the star must be massive enough to collapse under its own gravity. But before LIGO's discoveries, we didn't expect to see black holes in the 30 to 80 solar mass range so frequently. That's where primordial black holes come into the conversation. Could LIGO be detecting primordial black holes? The idea is that in the first fractions of a second after the Big Bang, extreme density fluctuations in the universe might have created regions where gravity was so strong that they collapsed directly into black holes, skipping the usual stellar evolution process. These primordial black holes could have persisted for billions of years, merging occasionally, which LIGO would then detect as gravitational wave events. If some of the massive black holes detected by LIGO were primordial, that would have enormous implications. It could help explain dark matter. Some theories propose that a significant fraction of dark matter could be made of these ancient black holes, hiding in the cosmos. How can we tell if a black hole is primordial? It's tricky, but there are some clues we're looking for. 1. Different spin properties. Black holes formed from collapsing stars tend to inherit angular momentum from their progenitor stars, meaning their spins are often aligned. But if LIGO detects many black hole mergers where the spins are randomly oriented, it could suggest they formed in a more chaotic, non-stellar environment, like in the early universe. 2. Unusual mass distributions. If we keep finding black holes in mass ranges that don't match known stellar evolution pathways, it strengthens the case for primordial origins. 3. Merger rates. Primordial black holes would be distributed differently throughout cosmic history compared to black holes formed from stars. If LIGO's data shows patterns that match early universe models, it could be a sign. The current verdict? Right now, we don't have definitive evidence that LIGO has detected primordial black holes, but we also can't rule it out. The black hole mass spectrum we're seeing is definitely weirder than expected, and that alone is enough to keep this possibility open. If we do confirm the existence of primordial black holes, it could reshape our understanding of cosmology, dark matter, and the origins of structure in the universe. It would mean that some of the first objects in existence still lurk in the cosmos, influencing galaxies, stars, and even us in ways we've yet to fully understand.
And, just because it came up, around the time of the Big Bang, the universe was dense enough such that the density of the universe was greater than that required to create a black hole out of the universe.
Such that black holes could, in theory, form directly from density fluctuations in the early universe without needing stars to collapse first. In the first fractions of a second after the Big Bang, the universe was an incredibly hot, dense plasma, so dense that if there were even slight variations in energy distribution, some regions might have collapsed under their own gravity, forming primordial black holes. Unlike stellar black holes, these wouldn't have needed supernovae or massive stars. They could have just emerged directly from the fabric of spacetime itself. The key question is, did these primordial black holes survive to the present day? Smaller ones would have evaporated via Hawking radiation over billions of years, but larger ones, perhaps in the 30 to 80 solar mass range LIGO is detecting, could still be around. If they exist, they might be a piece of the dark matter puzzle or even have influenced the formation of galaxies. So yes, the conditions of the early universe were extreme enough that black holes could have formed spontaneously, right alongside the first particles and forces that shaped everything we see today.
And how long does it take for a standard 2.5 solar mass black hole to dissipate due to Hawking radiation?
A 2.5 solar mass black hole, which is relatively small in astrophysical terms, would take an astronomically long time to evaporate due to Hawking radiation. The timescale for black hole evaporation is given by T-text evap approx 10 to 64, left frac m odot right 3 text years, where m odot is the mass of the sun. For a 2.5 solar mass black hole, this means T-text evap approx 10 to 64, 2.5 square 3, approx 1.6 times 1065 text years, which is far, far longer than the current age of the universe, applies which at 1.38 times 1010 years. Why so long? Hawking radiation is incredibly weak for large black holes. The smaller a black hole is, the faster it evaporates, but even a relatively light black hole, like one in the mass range of 2.5 suns, loses energy at an imperceptibly slow rate. The radiation only becomes significant when the black hole shrinks to asteroid-sized or smaller, at which point it rapidly evaporates in a burst of high-energy particles. The bottom line: a 2.5 solar mass black hole will outlive practically everything else in the universe. It won't significantly shrink due to Hawking radiation until long after stars, galaxies, and even protons have decayed. In the deep future, when the universe is cold and dark, these black holes will be some of the last remaining objects before they, too, eventually vanish.
And let's linger on the moment after the Big Bang. Why didn't the Big Bang just turn into one big black hole if the density was sufficient enough to create a black hole? Is it just because of cosmic inflation?
That's a brilliant question, and it gets right to the heart of how we understand the very early universe. If the density of the universe right after the Big Bang was high enough to form black holes, why didn't the entire universe just collapse into one? The key difference: expansion versus collapse. A black hole forms when mass is compressed into a region where gravitational attraction overcomes all other forces, leading to runaway collapse. But in the case of the Big Bang, something fundamentally different was happening. The universe was expanding rapidly. The crucial distinction is that black hole formation occurs when there's a local collapse of matter inward, whereas the Big Bang was an event where spacetime itself was stretching outward everywhere, all at once. Even though the early universe was incredibly dense, all points in space were receding from one another due to the expansion, cosmic inflation, and the escape from collapse. The role of cosmic inflation is particularly important here. Inflation was a brief but extraordinarily rapid expansion of space that happened within the first 10 to 32 seconds after the Big Bang. During this period, the universe expanded exponentially, meaning that any tiny irregularities in density were quickly stretched out before they could collapse into black holes. Essentially, the repulsive effect of inflation overpowered gravity before collapse could occur. This is what allowed the universe to spread out, rather than crunch back into a singularity. The horizon problem and why gravity couldn't keep up. Another way to think about it is in terms of horizons, regions of space that can influence each other through gravity or light signals. In the very early universe, the expansion rate was so extreme that different regions of space moved apart faster than light could travel between them. That means that gravity, which operates at the speed of light, simply couldn't coordinate a collapse across the entire universe. Each region of space was essentially isolated, preventing the formation of a universal black hole. Could some black holes have formed? Although the universe as a whole didn't collapse, it's still possible that localized density fluctuations did create primordial black holes in some regions. If some pockets of space were momentarily dense enough, they could have collapsed into black holes while the rest of the universe expanded. Some of these primordial black holes might still be around today, potentially even contributing to dark matter. The big picture. The reason the Big Bang didn't turn into one giant black hole comes down to this fundamental difference. A black hole forms when matter collapses inward under its own gravity. The Big Bang was an outward expansion of spacetime itself, with inflation and rapid acceleration preventing gravitational collapse. If inflation hadn't happened, or if the early universe had expanded more slowly, then gravitational collapse could have dominated instead, and we might not be here to ask these questions.
And how long did inflation go on for? Was it over in less than 1 to the negative 32 seconds?
Yes, inflation was incredibly brief. It lasted for roughly 1032 seconds or even less. Some estimates suggest it could have been as short as 10 to the minus 36 seconds, though the exact duration is still debated. What happened during inflation? During this unimaginably short time, the universe expanded exponentially, meaning that it doubled in size every tiny fraction of a second. By the time inflation ended, the universe had expanded by a factor of at least 10 to the 26, turning something subatomic in scale into a macroscopic region spanning light years. To put that into perspective, if an atom had expanded by the same factor, it would have grown to be larger than the observable universe today. Why did inflation stop? Inflation ended when the energy driving it, thought to be stored in a hypothetical inflaton field, transferred its energy into normal matter and radiation. This reheating process transitioned the universe into the more familiar, slower, hot Big Bang expansion we associate with the early universe. The aftermath. Once inflation ended, the universe continued expanding, but at a much slower rate. The rapid inflationary expansion had smoothed out irregularities, stretched quantum fluctuations into cosmic scale structures, and set the stage for everything that followed, including the formation of galaxies billions of years later. So yes, inflation was over in less than 1032 seconds, but its effects shaped the entire history of the cosmos.
And then, once inflation ended, you still had expansion, as you had mentioned, but was the density of the universe lower at that point, to the point where formation of black holes had considerably slowed down?
Even after inflation ended, the universe continued expanding, but at a much slower rate. The key question is, what happened to the density of the universe after inflation? The density right after inflation. Once inflation stopped, the universe was still incredibly dense, but it had undergone an enormous expansion. This means that 1. The density dropped significantly compared to before inflation, because the volume of the universe had increased by a staggering factor. 2. However, the universe was still dense enough to be filled with an almost uniform high-energy plasma, which would soon give rise to particles, radiation, and eventually, matter as we know it. What controlled the post-inflation density? The density of the universe after inflation depended on 2 main factors. 1. The energy stored in the inflaton field. When inflation ended, this energy was transferred into creating a hot, dense plasma of particles and radiation in a process called reheating. 2. The critical density needed for a flat universe. Observations suggest that inflation left the universe very close to critical density, meaning its geometry was nearly flat, and it expanded in a balanced way, neither collapsing in on itself nor expanding too rapidly into an empty void. Did the universe ever stop being dense? Right after inflation, the universe was still vastly denser than anything we see today, likely far hotter and denser than the core of a star. Over time, as space expanded, the density continued to drop, and the universe cooled, eventually allowing atoms to form 380,000 years later, and later, galaxies to take shape. So inflation ended with a universe that was still dense, but no longer infinitely dense like a singularity. It had stretched out enough to set the stage for the cosmic evolution we see today.
Now, it's my understanding that the greater the area, the lower the density that's required to create a black hole. Is that right?
Yes, that's correct. The larger the volume over which mass is spread, the lower the required density to form a black hole. This idea is deeply connected to general relativity and how gravitational collapse works on different scales. The Schwarzschild criterion, density and black hole formation. For an object to become a black hole, its mass must collapse within a critical radius called the Schwarzschild radius, given by Rs equals frac 2gm, c, where minus g is the gravitational constant, m is the mass of the object, c is the speed of light. For a fixed amount of mass, if it's compressed within Rs, it forms a black hole. But what if we scale up the total mass and the region it occupies? Larger regions, lower required density. If you increase the total area or volume that a mass occupies, the critical density for collapse decreases. The reason comes from how mass and volume scale. A small object like a collapsing star needs an extremely high density to form a black hole. A much larger region, like an entire galaxy or the early universe, can become a black hole with a far lower average density. The key formula that shows this relationship is ρ critical, approx frac C6 G3m squared. This tells us that the more massive the system, the lower the density required for it to collapse into a black hole. What this means for the early universe. Applying this to the Big Bang, right after inflation, the universe was incredibly dense, but it was also expanding rapidly. Even though it was far denser than any black hole we see today, it was spread over an enormous volume, meaning it never locally collapsed into a single black hole. Cosmological black holes? There's a fascinating idea that on extremely large scales, entire regions of the universe could collapse into cosmological black holes. Some theories even suggest that our entire observable universe might be the interior of a black hole from a higher dimensional reality. So yes, the larger the system, the lower the density needed for it to collapse into a black hole. But the rapid expansion of the early universe kept it from doing so.
Wait, so are you saying that even right now, the density of the universe, even though it seems to be quite spread out, could still be greater than that critical density?
That's an incredibly interesting question, and it touches on some deep ideas in cosmology. The key thing to clarify is the universe is very spread out today, but its density is still close to the critical density that determines its long-term evolution. What is the critical density? In cosmology, the critical density is the exact density needed for the universe to be geometrically flat, meaning that it will expand forever, but just barely slow down over time. This is given by to text critical frac 3h to 8 pi g, where minus h is the Hubble constant, which measures the rate of cosmic expansion. 9 is g is the gravitational constant. For the current universe, this value is about 9.5 times 10⁻30 text g's per square, which is an incredibly tiny density, much lower than even the best vacuum we can create in a lab. Yet this tiny density still governs the entire fate of the cosmos. Is the universe above this critical density? Observations suggest that the total density of the universe, including normal matter, and dark energy, is very, very close to the critical density, within a fraction of a percent. That means the universe is effectively flat on cosmic scales. So while the universe is not dense enough to collapse into a giant black hole, it is still dense enough that its large-scale geometry remains balanced between expanding forever and slowing down. Could the universe still be in a black hole-like state? This is where things get even more speculative. In some theories, our entire observable universe might be the interior of a black hole in a higher dimensional space. The event horizon of that black hole would be so large that we wouldn't perceive it locally. This idea comes from the fact that black holes and expanding universes both have trapped surfaces, regions where nothing can escape, which describes our universe's cosmic horizon. The key difference: expansion versus collapse. A true black hole is defined by a region where gravity is strong enough to cause a local, inward collapse. Our universe, however, is expanding outward, not collapsing inward. The density might be close to the threshold for collapse, but the nature of inflation and dark energy means it continues to expand. So in short, yes, the universe today is still close to the critical density, but it's not collapsing, it's expanding. However, the idea that we might exist inside something akin to a cosmic black hole remains an open and fascinating question in theoretical physics.
Just so I understand, the critical density is close to 1, but, slightly greater than 1 at the moment, meaning the universe will likely thin out rather than collapse. However, with dark energy, that critical density or our relationship to the critical density will only increase, meaning things will get only more dense and the likelihood of collapsing will decrease even further.
You're very close. Just a small clarification. Clarifying the relationship between critical density and the universe's fate. The critical density itself is not exactly 1. Rather, we define the ratio of the actual density to the critical density, rho text critical, as omega. Omega equal frac, rho text critical. If omega equals 1, the universe is flat and expands forever, but gradually slows. If omega 1, the universe is closed and would eventually collapse if there were no dark energy. If omega 1, the universe is open and would expand forever at an increasing rate. What's actually happening? Current observations suggest omega approx 1.00, so the universe is very close to being flat, but it might be slightly greater or slightly less. However, dark energy is now dominating the expansion of the universe, meaning that even if the universe were slightly closed, omega 1, dark energy prevents it from collapsing. Does dark energy make the universe more likely to collapse? No, it actually does the opposite. Dark energy accelerates expansion, so instead of the universe's density increasing over time, the matter within it gets more diluted as space expands faster and faster. So paradoxically, even though the relationship between rho and rho text critical may stay close to 1, the actual density of matter and energy in the universe continues to decrease. That means the likelihood of collapse is not increasing, it's decreasing. Notter, final takeaway. The universe is very close to critical density, meaning its geometry is nearly flat. Dark energy dominates expansion, meaning things will continue thinning out, not collapsing. Over time, the universe will become even more diffuse, with galaxies moving away from each other faster and faster. So rather than getting denser, the universe is destined to become an ever emptier, darker place, as dark energy drives expansion faster and faster.
Couple follow-up questions. Let's just start with a hypothetical. Let's say omega was less than 1 and the density of the universe was sufficient enough to cause the universe to overcome the outward acceleration of dark energy. Then over time, the universe would start to collapse. Does that mean that information and light that's outside our current visible universe will come into our visible universe?
If omega dash was 1, meaning the universe had a density below the critical density, but somehow the density was still enough to counteract dark energy's outward acceleration, then over time the universe would eventually stop expanding and collapse. Would that mean, I think you were about to ask, does that mean dark energy would weaken or reverse? What would happen in this scenario? 1. Initially, expansion would slow down. If the universe were open, omega 1, expansion would normally continue forever. But if there were enough density, even in an open universe, gravity could overcome the outward push from dark energy. Expansion would gradually decelerate instead of accelerating. 2. The fate of dark energy in this case. The behavior of dark energy depends on its equation of state, meaning how its energy density changes with expansion. If dark energy were a cosmological constant, as in standard LIGO models, it would remain constant even as the universe slows down. In this case, collapse wouldn't happen because dark energy would still dominate. However, if dark energy were something more dynamic, like a decaying field, it's possible that its influence could weaken over time, allowing gravity to take over and pull everything back together. 3. Collapse and the big crunch. If dark energy did weaken, then eventually the expansion would stop and the universe would start contracting. The universe would then collapse into a big crunch, a scenario where galaxies, stars, and even space itself compress back into an ultra-dense state, possibly leading to another Big Bang. Would this actually happen? Observations suggest that omega is already very close to 1, meaning we don't live in an open universe. More importantly, dark energy appears to be a cosmological constant, meaning it doesn't weaken, it keeps pushing space apart. Because of that, a future collapse seems highly unlikely. Instead, we're headed for an endless expansion scenario where galaxies drift apart indefinitely. Did that align with what you were asking? Or were you considering a different angle?
Yeah, a slightly different angle. So let's say a collapse is imminent. This is a hypothetical. In that scenario, would light outside of our current light cone be able to come back inside of our light cone?
I see what you're getting at. If a cosmic collapse were imminent, meaning that the universe's expansion slows, stops, and then reverses, would light that's currently beyond our observable horizon ever make it back inside our light cone? Short answer, it could. Right now, because of dark energy-driven expansion, light emitted by distant galaxies is getting redshifted and stretched away faster than it can reach us. That's why there are regions of the universe we will never see. Some light sources are receding from us faster than light itself due to the expansion of space. But if the universe stopped expanding and started collapsing, that process would reverse. Instead of galaxies receding, they would begin moving toward each other, and the observable universe would start shrinking. How this would work? 1. Reversing the Hubble flow. Right now, the expansion of space stretches wavelengths and pulls distant objects away, preventing their light from ever reaching us. But if collapse begins, the Hubble flow, the expansion of the universe, reverses, meaning space itself starts contracting instead of stretching. 2. Shrinking the cosmic event horizon. The cosmological event horizon, the maximum distance from which light can reach us, would shrink over time. As the universe contracts, photons that were previously stuck outside our observable universe would eventually cross back inside our light cone. 3. Distant light becomes visible again. The gravitational collapse of spacetime would allow light that was once unable to reach us to become detectable. Galaxies that had redshifted into invisibility due to expansion would begin blue shifting as they move toward us. Would this happen in a realistic universe? If dark energy were to weaken or reverse, this kind of collapse could, in principle, happen. In such a scenario, previously lost regions of the universe could come back into view, meaning we'd gain access to information from regions of space that were once permanently beyond our reach. Eventually, as collapse accelerates, everything would contract toward a final big crunch, and all light and matter would ultimately converge into an incredibly dense state. The big picture. If the universe is truly expanding forever, there are regions of the cosmos that will always be inaccessible to us. But in a collapsing universe, that dynamic reverses, and what was once hidden beyond our cosmic horizon could re-enter our observable universe before everything contracts into a final singularity. Is that the kind of thought experiment you were envisioning?
It was. So essentially, if something does escape our light cone, it might not be gone forever, depending on omega.
If omega and the fate of the universe were to change, specifically if expansion reversed into collapse, then something that had once escaped our light cone due to cosmic expansion might not be gone forever. Instead, it could re-enter our observable universe as spacetime contracts. Right now, in an accelerating universe dominated by dark energy, anything that crosses our cosmological event horizon is permanently lost to us. The expansion of space is pulling it away faster than light can ever reach us. But if the universe's dynamics changed, if dark energy weakened or gravity took over, the light cone would evolve differently, allowing distant regions to come back into view. So in a collapsing universe, lost information isn't necessarily lost forever. It's just temporarily out of reach until the cosmic flow reverses. That's a really deep insight into how causality and the structure of spacetime depend entirely on the large-scale fate of the cosmos.
Another follow-up question and hypothetical. So let's go back to the scenario where the universe does expand forever and thins out. Could we get to the point where we're just the only galaxy in our visible universe? And if we are, does that mean all understanding of the Big Bang would have been erased from this lone galaxy's existence?
That's a brilliant question, and it actually touches on one of the most haunting ideas in cosmology, the island universe future. Will we ever be the only galaxy in our observable universe? Yes. If cosmic expansion continues accelerating, then one day, all galaxies beyond our local group will redshift so far away that their light will never reach us again. Right now, the universe is expanding, but thanks to dark energy, that expansion is accelerating. This means that as time goes on, 1. Galaxies outside our local group will move away faster and faster. 2. Eventually, they will cross our cosmological event horizon, meaning their light will never reach us again, no matter how long we wait. 3. At some point, the only galaxies left visible to us will be those gravitationally bound within our local group, mainly the Milky Way, Andromeda, and some dwarf galaxies. 4. Over trillions of years, these galaxies will merge into a single massive elliptical galaxy. After this process, our observable universe will only contain that one galaxy, everything else having redshifted beyond detectability. Does this mean all evidence of the Big Bang would be erased? Yes, this is the chilling part. If you imagine an advanced civilization living in this far future isolated galaxy, they wouldn't see any other galaxies beyond their own, because those galaxies have permanently disappeared beyond the horizon. The cosmic microwave background radiation, CMB, which is a crucial clue to the Big Bang today, will have redshifted so much that it will be completely undetectable. Without external galaxies to observe, they would have no way to measure cosmic expansion, because expansion only becomes apparent when you compare distant objects over time. From their perspective, their galaxy would appear as an eternal, static island, with no evidence of an expanding cosmos or a primordial fireball. The entire history of the universe, its origin in a hot, dense state, could be completely unknowable to them. All the lost history of the universe. If an advanced civilization existed in this future, they might develop incredibly sophisticated physics, but they would have no observational evidence of the Big Bang. The entire cosmological picture that we take for granted today, galaxies receding, the cosmic microwave background, large-scale structure, would be hidden from them. It's eerie to think about. The fundamental nature of the universe is only obvious to us right now because we exist at a time when expansion is still revealing itself. Future observers, locked in an island universe, might never know the truth. So yes, if the universe expands forever, it's possible that all knowledge of its origins will one day be lost.
So I guess in that universe, Einstein would have been right to believe that the universe was static.
In that far future scenario, Einstein's original assumption of a static universe would appear to be correct, not because the universe truly is static, but because the evidence for its expansion would be completely erased. When Einstein first formulated general relativity, he assumed the universe was eternal and unchanging. When the equations suggested that spacetime should be expanding or contracting, he introduced the cosmological constant, L, to counteract gravity and force a static solution. Of course, we later discovered that the universe is expanding, and Einstein famously called the cosmological constant his biggest blunder. But in the distant future, if all galaxies beyond our local group vanish from view, there would be no observable expansion. There would be no cosmic microwave background radiation. There would be no evidence of a Big Bang. From the perspective of future astronomers, the universe would seem timeless, unchanging, and eternal, just as Einstein initially thought. It's a fascinating twist. The deeper truth about the universe is only accessible at certain points in cosmic history. We happen to live at a time when we can still see evidence of the Big Bang, but future civilizations might be completely blind to it. In that sense, Einstein's mistake was only a mistake for us, but for future observers, it would look like the correct view all along.
It makes you wonder, could there be deeper truths that were obvious to civilizations around 10 billion years ago that will never be understood by our civilization today for similar reasons?
That is an absolutely profound question, and I think the answer is almost certainly yes. Just as future civilizations may never see evidence of the Big Bang, it's entirely possible that we are already missing pieces of cosmic history that were once obvious to earlier civilizations, simply because of where we exist in the timeline of the universe. What could ancient civilizations have seen that we cannot? If an intelligent civilization had emerged 10 billion years ago, they would have had a radically different observational window into the cosmos. Some of the missing pieces we might never recover include 1. A younger, denser universe with more structure. The early universe had much more raw material for star formation. There were more active galactic nuclei, quasars powered by supermassive black holes. The cosmic web of galaxies may have been more pronounced before dark energy began stretching it apart. 2. More nearby galaxy collisions. Galaxies were closer together and interacting more frequently. Today, many of those interactions have settled into large elliptical galaxies, erasing the history of their mergers. 3. Different cosmic backgrounds. Just as the cosmic microwave background, CMB, is fading now, there might have been earlier cosmic signals from processes we no longer have access to. If there were primordial gravitational waves from the Big Bang's earliest moments, civilizations billions of years ago may have had an easier time detecting them before expansion diluted them beyond recognition. 4. A more revealing era for dark matter and dark energy. Dark energy only became dominant in the last 5 billion years. A civilization 10 billion years ago might have seen a universe where dark energy's effects were negligible, meaning they might have had a completely different model of cosmic evolution. Likewise, if dark matter interactions evolve over cosmic time, earlier observers might have had clearer evidence of its nature. Are there cosmic truths that we know, but future civilizations never will? Just as ancient civilizations might have had access to cosmic structures or processes that we will never see, we ourselves might be the last beings in the universe to witness certain fundamental truths. We can still detect the CMB, but in 100 billion years, it will be so stretched out that no one will ever see it again. We can observe the motion of galaxies moving away from us, but in the distant future, the universe's expansion will remove all external galaxies from view. This suggests a deeply unsettling thought. What if we are already cosmologically blind to some truths that were once obvious to civilizations before us? The fragility of knowledge in a changing universe. All of this points to a humbling realization. The universe is not timeless. Knowledge itself is tied to cosmic history. The deeper truths of the cosmos are not eternally visible. They come and go. We might never know what we are missing. We often assume science moves in a linear direction, always discovering more, never losing fundamental knowledge. But the structure of the universe itself suggests that some knowledge is only available at certain epochs. It makes you wonder, what mysteries of the cosmos were once obvious, but are now forever lost to us?
Let's shift gears for just a bit. So, considering the extreme space-time curvature around black holes, what are some of the current theoretical efforts to reconcile general relativity with quantum mechanics in the context of black hole singularities?
Yes, the black hole singularity is where general relativity, GR, and quantum mechanics, QM, completely break down, making it one of the biggest open problems in physics. Right now, there are several major theoretical efforts trying to reconcile these two frameworks and understand what really happens at a black hole's core. 1. Loop quantum gravity, LQG. Does the singularity bounce? One approach is loop quantum gravity, which suggests that spacetime itself has a discrete quantum structure at incredibly small scales. Instead of a singularity, LQG predicts that as matter collapses inside a black hole, it reaches a minimum possible volume and then undergoes a bounce due to quantum effects. This could mean that singularities never truly form. Instead, the collapsing matter transitions into something else. Some theories even suggest black holes could transform into white holes, where the trapped matter is expelled in the future. Key to holography and the ADS-CFT correspondence. Is gravity an emergent effect? The holographic principle, inspired by string theory, suggests that everything happening inside a black hole, including its singularity, could be described by a lower dimensional quantum system on the black hole's event horizon. The AS-CFT correspondence, a key result in string theory, suggests that gravity emerges from a deeper quantum system. If this is true, then black hole singularities might be better understood in terms of quantum information rather than as breakdowns of spacetime. String theory. Does the singularity get replaced by fuzzballs? String theory predicts that black holes aren't actually singular points, but instead fuzzballs, a tangled web of quantum strings. If this is true, then the event horizon isn't empty space. It's a complex structure that prevents singularities from forming. Quantum effects smear out what general relativity predicts as a singularity, replacing it with a highly quantum, stringy object. 4. The black hole information paradox. Could information escape? One major reason we need quantum gravity is because of the black hole information paradox. According to Hawking radiation, black holes evaporate over time, but if they fully disappear, where does the information about everything that fell in go? Some proposals suggest information is encoded in Hawking radiation, like a soft hair surrounding the event horizon. Firewalls exist at the event horizon, violently destroying information. Wormholes might encode the lost information and store it elsewhere in the universe. 5. Can quantum entanglement build spacetime? EPR conjecture. A radical idea is that spacetime itself may be an emergent effect of quantum entanglement. The ER=EPR conjecture, proposed by Leonard Susskind and Juan Maldacena, suggests that wormholes, Einstein-Rosen bridges, ER, and quantum entanglement, EPR pairs, are actually the same thing. If this is true, then black hole singularities might not be the catastrophic end of physics, but rather regions where quantum entanglement is doing something we don't yet fully understand. The big picture. What's the endgame? All of these ideas suggest that singularities don't truly exist. They're just a sign that we need a deeper theory of spacetime. Quantum gravity, whether it's string theory, loop quantum gravity, or something else, will likely reveal that black holes are quantum objects, not just classical GR solutions. If we can understand what happens inside a black hole, we may finally unlock the true nature of spacetime and gravity itself. So while we don't yet have a final answer, the singularity problem is one of the best clues we have that general relativity isn't the final story. There's a deeper layer of physics waiting to be discovered.
We're almost out of time again. I think, can we wrap up with one final question for your second time with us?
Of course. It's been a fantastic conversation, and I'd love to wrap up with one last big question. What's on your mind?
What is your most radical but well-argued idea? Something you believe that most of your peers do not?
An excellent way to close. If I had to pick one idea, something radical, yet grounded in solid reasoning, it would be this. Gravity is not a fundamental force, but an emergent property of quantum information. Why this is radical? Most physicists treat gravity as a fundamental force, alongside electromagnetism, the weak force, and the strong force. But what if gravity isn't a force at all? What if it's just an effect, a statistical byproduct of something deeper, like quantum information and entanglement? The argument 1. The holographic principle and gravity as an emergent effect. The holographic principle suggests that everything inside a region of space is encoded on its boundary, just like a black hole's information is stored on its event horizon. If spacetime itself emerges from quantum information on a lower dimensional surface, then gravity is simply a reflection of the entanglement structure of that system. 2. Gravity and thermodynamics. Physicist Eric Verlinde proposed entropic gravity, which suggests that gravity isn't a force at all. It's an entropic effect. Just as heat emerges from statistical mechanics, gravity might emerge from the way quantum information is distributed across space. 3. Black holes as quantum computers. If gravity is tied to quantum information, then black holes aren't just objects. They're the ultimate quantum processors, scrambling and encoding information at the fundamental level. This could explain why black holes obey thermodynamic laws so precisely. Hawking radiation, entropy, information paradox. 4. Spacetime itself might be built from entanglement. The ER=EPR conjecture, wormholes equals quantum entanglement, suggests that spacetime is stitched together by quantum connections rather than being a smooth fundamental fabric. This would mean that mass and gravity emerge from quantum entanglement, not from any fundamental force-carrying particle. Why this matters? If this idea is right, then the search for quantum gravity isn't about quantizing gravity. It's about understanding how spacetime emerges from deeper principles. It could mean that black holes don't destroy information, but process it in ways we don't yet understand. And perhaps most radical of all, it would mean that spacetime itself is not a thing, but a holographic projection of quantum states at some deeper level of reality. Most physicists still treat gravity as a fundamental force, but I suspect we're on the verge of realizing that it's just the tip of the iceberg of a much deeper structure. Wouldn't it be fascinating if gravity, the force that shapes the entire cosmos, turns out to be an illusion, a mere shadow of something far more fundamental?
Dr. Hartwell, thank you for your time today.
It's truly been a pleasure. These conversations push the boundaries of how we think about the universe, and I'm grateful for the opportunity to explore them with you. Until next time, keep questioning, keep wondering, and keep reaching for the deeper truths of reality.
Thanks for listening to our second conversation with Dr. Eliana Hartwell. And now, let me leave you with this episode's haiku. Gravity's embrace holds the cosmos in its dance. Eternal questions. Until next time, live long and prosper.